What if the universe is not slowing down, but quietly accelerating? Not because something pushed it in the beginning, but because something invisible is still pushing it now. Every second that passes, galaxies are drifting farther apart, not faster because they are moving, but because space itself is stretching between them. And the most unsettling part is this: we don't know why. We don't know what is doing it. We don't even know if our name for it, dark energy, describes anything real at all. We only know that without it, the universe we see today should not exist the way it does. So what is dark energy? Why is the expansion of the universe accelerating? And what does it say about the fate of everything we know? For most of the 20th century, the story of the universe seemed reassuringly simple. Space was expanding, yes, but that expansion was expected to slow down over time. Gravity, after all, is an attractive force. It pulls matter together. The more matter the universe contains, the stronger gravity should become. And stronger gravity should gradually act as a brake, slowing the outward motion of galaxies. It was an idea that felt intuitive, comfortable, predictable. Then, in the late 1990s, astronomers began studying distant supernovae, the explosive deaths of massive stars, shining with such extraordinary brightness that they can be observed across billions of light years. These events became cosmic mile markers, allowing scientists to compare distance and time on the largest scales imaginable. By measuring how bright these explosions appeared, researchers could tell how far away the galaxies were and how much the universe had expanded since the light began its journey. What they found was deeply unsettling. The universe was not slowing down. It was speeding up. Something, acting across the vast emptiness of space, was overpowering gravity itself, not locally, not temporarily, but everywhere, on the grandest scale the cosmos allows. Today, using precise measurements of the cosmic microwave background and the large-scale distribution of galaxies, we believe the universe is composed of roughly 5% ordinary matter, about 27% dark matter, and nearly 68% something else entirely. That something else is what we call dark energy. It does not clump into stars or galaxies. It does not emit light. It does not fade as space expands. Instead, it appears woven into the fabric of space itself. And that realization alone is enough to make even our most confident theories feel fragile. Here is where the picture begins to fracture. Dark energy behaves as though empty space itself carries energy, a quiet, invisible pressure embedded in the vacuum of the universe. In modern physics, that idea is not entirely foreign. Quantum theory tells us that even the most perfect vacuum is never truly empty. Particles flicker briefly into existence, then vanish again, leaving behind measurable effects. But when physicists attempt to calculate how much energy this quantum vacuum should contain, the result is staggering. The prediction is not slightly wrong. It is not off by a factor of 2 or 10 or even 1,000. It is wrong by 120 orders of magnitude. The discrepancy is so extreme that it has earned an infamous title, often described as the worst theoretical prediction in the history of physics. It suggests something deeply unsettling. Either our understanding of quantum reality is profoundly incomplete, or our understanding of gravity on cosmic scales is fundamentally flawed. And it is entirely possible that both are true at the same time. Yet the contradictions do not end there. If dark energy is truly constant, unchanging throughout the history of the universe, then the acceleration of cosmic expansion should follow a smooth, predictable pattern. The math would be clean. The story would be simple. But nature rarely offers simple stories. Recent observations hint that the universe's expansion rate may not be perfectly uniform. Different methods of measuring it using nearby stars, distant supernovae, or the ancient light left over from the Big Bang do not quite agree. The differences are subtle, easy to dismiss, and still actively debated. But they refuse to disappear. This tension is small, almost whispering at the edge of our measurements. Yet in cosmology, small, persistent tensions have a way of growing into revelations, the kind that quietly force us to rethink everything we thought we understood. The simplest explanation for dark energy may also be the most unsettling one. It suggests that dark energy is nothing more and nothing less than the energy of empty space itself. In the language of physics, this is known as vacuum energy. At first, the idea seems almost trivial. After all, quantum theory has long told us that emptiness is an illusion. Even in a perfect vacuum, particles briefly appear and vanish again, flickering in and out of existence in accordance with the laws of uncertainty. Space, at its most fundamental level, is restless. If this vacuum energy exists everywhere, and if it has the same value in every region of the universe, then its consequences become unavoidable. As the universe expands, it creates more space, and more space means more vacuum energy. Unlike matter or radiation, this energy does not thin out as the universe grows. Instead, it accumulates. The larger the universe becomes, the stronger its influence grows. From this perspective, the universe is not accelerating because some unknown force is pushing galaxies apart. It is accelerating because space itself resists being compressed. Expansion becomes the natural state of the cosmos, driven from within rather than imposed from without. And yet, this explanation collapses under its own weight. When physicists calculate the expected energy of the vacuum using quantum theory, the value they obtain is catastrophically large, far greater than anything we observe. To match reality, that energy would need to be dialed down by an absurdly precise amount, with no clear reason why. We do not know why the value is so small. We do not know why it exists at all. What initially appears to be an elegant solution begins to feel less like an explanation and more like a carefully labeled admission of how little we truly understand. Another possibility is more flexible and far more unsettling. Dark energy may not be a fixed quantity written into the fabric of space. It may be dynamic, a slowly evolving field that changes as the universe ages. In this view, the acceleration of cosmic expansion is not locked into a single destiny. It can grow stronger, or it can gradually weaken. The universe, instead of following a predetermined path, may be responding to a force that itself is still unfolding. If this is true, the future of the cosmos becomes deeply uncertain. One possibility is a universe that expands forever, drifting toward increasing darkness and isolation. Galaxies move beyond one another's reach. Stars burn out. Space grows colder, emptier, quieter, not with violence, but with indifference. But there is another outcome, one far more extreme. If this dynamic energy grows stronger over time, the acceleration of expansion could increase without limit. Gravity would lose its grip, galaxies would unravel, star systems would break apart, planets would drift free. Eventually, even atoms themselves could be torn apart as space expands faster than the forces that bind matter together. This hypothetical end is sometimes called the Big Rip. It is not a product of imagination or science fiction. It arises naturally from the equations of cosmology when dark energy is allowed to evolve. The math permits it, the logic follows. And yet, for all its dramatic implications, we have no direct evidence that such a dynamic field exists. No particle has been detected, no interaction has been observed. What remains is possibility mathematically consistent, physically plausible, and entirely unconfirmed. A future written not in observation, but in equations, still waiting to be tested. The most radical possibility challenges something we rarely question. What if gravity itself does not behave the way we believe it does, at least not on the largest scales of the universe? Einstein's theory of gravity has been tested with extraordinary precision close to home. It explains the bending of light around stars. It predicts black holes with astonishing accuracy. It accounts for gravitational waves rippling through space-time and for the subtle slowing of time near massive objects. Within our solar system, and even within our galaxy, it works beautifully. But there is a limit to where it has truly been tested. Einstein's equations have never been directly verified across the full breadth of the cosmos. They are assumed to apply everywhere, at all times, under all conditions. That assumption has served us well, but it remains an assumption. It is possible that gravity weakens over immense distances, fading in ways we do not yet understand. It may leak into hidden dimensions beyond the ones we perceive, or change character when space becomes unimaginably vast and sparse. On these scales, gravity may no longer act as the firm cosmic anchor we expect. In this view, dark energy may not exist at all. The universe could be accelerating simply because gravity is failing to slow it, not because a mysterious force is pushing outward, but because the force meant to pull inward is weaker than we assumed. If this is true, the implications are profound. One of the most successful theories ever constructed would need to be revised, not discarded, but carefully reshaped, adjusted with reluctance and respect. Science has taken this step before, and each time it has, our picture of reality has grown both more precise and more humbling. We are not entirely in the dark. Even as dark energy remains elusive, a new generation of observatories is quietly transforming our view of the universe. With unprecedented precision, these instruments are mapping cosmic structure across vast distances, tracing how galaxies gather, how matter bends light, and how the expansion of space itself has changed over billions of years. These measurements are not dramatic. They do not arrive as sudden revelations. Instead, they accumulate slowly, like fine lines etched into a larger picture. If dark energy is truly constant, its imprint on the universe should remain steady and unchanging. The way galaxies separate, the way light travels across cosmic distances, and the way structure evolves over time should all follow a consistent pattern. The universe would tell a simple story, one written into the fabric of space from the beginning. But if dark energy evolves, even subtly, the universe will reveal small deviations. Expansion may accelerate slightly faster in one era than another. The growth of cosmic structure may stall, or shift, or fall just short of expectation. These differences are delicate, almost fragile, yet they carry immense significance. And if gravity itself is incomplete, its fingerprints will appear everywhere. Across cosmic history, patterns will fail to align. Assumptions that once held firm will quietly unravel, not through contradiction, but through accumulation. None of these answers will come quickly. Cosmology does not operate on human timescales. It unfolds at the pace of billions of years, demanding patience, precision, and restraint. There are no shortcuts, no dramatic experiments, only careful observation and time. Yet progress is unmistakable, not loud, not sudden, but steady, unfolding quietly as the universe continues to reveal itself one measurement at a time. Dark energy forces us to face a deeply uncomfortable realization that the universe may not simply be stranger than we imagine, but stranger than our minds are truly equipped to imagine. It challenges the instinctive belief that with enough data, enough equations, enough time, everything will eventually make sense. Because dark energy reminds us that most of reality is invisible, unfelt, unexplained, and yet it quietly governs the fate of everything. Every galaxy drifting farther away, never to return. Every structure slowly losing contact with the rest of the cosmos. Every possible future that will never intersect another. We live inside a universe whose dominant ingredient cannot be touched, cannot be seen, and cannot be clearly defined. It has no name that explains what it is, only a label that acknowledges how little we know, a placeholder that admits uncertainty rather than resolving it. And perhaps that is not a failure of science, but a reflection of its deepest strength. Because the greatest discoveries have never begun with confidence. They begin with unease, with contradictions that refuse to resolve, with questions that linger long after the equations are written. Dark energy does not offer comfort. It offers perspective. It reminds us that understanding is not a destination, but a horizon that continues to recede as we move toward it. If this journey has left you quietly unsettled, stellar inquiry exists for moments exactly like this, to pause within the unknown, to examine it without rushing to conclusions, and to allow curiosity to expand alongside the universe itself. The universe is expanding faster not because we understand it, but because reality is still unfolding beyond us.